Okay, in this video, we're going to look at the velocity and acceleration vector functions. The velocity vector function is the derivative of the position vector function. And the key to understanding that, of course, is to understand the difference quotient. So what is r of t plus h minus r of t? It's the vector you add to r of t to get r of t plus h. So the geometric interpretation of r of t plus h minus r of t is the vector from p to q. And once you divide that by h, assuming h is a small number, you see how r of t plus h minus r of t over h is longer than r of t plus h minus r of t, because you're dividing by a small number. Anyway, as h gets close to 0, this difference quotient vector gets closer and closer to r prime of t, which is the velocity vector tangent to the curve of p. And then the magnitude of the velocity vector is a function of t, which will give you the speed. The acceleration vector is the derivative of the velocity vector. Let's look at an example here. Suppose we're in R2 here, I guess. Our position vector is t cubed, comma t squared. So the velocity vector would be 3t squared, comma 2t. The acceleration vector would be 6t, comma 2, and the speed would be the magnitude of the velocity vector. So let's take a little closer look at that. This is an animation that shows the position vector, the velocity vector, and the acceleration vector for the vector valued function we were looking at, t cubed, comma t squared. So for the position vector, remember the position vector is just telling you where the point is on the curve. So as the point moves from left to right, the position vector is getting smaller, and now the position vector is getting bigger. So the distance is going to be decreasing, then it's the distance. The magnitude is going to be decreasing, and the magnitude is going to be increasing, right? So for the velocity vector, the velocity vector the magnitude of it is very large. It's decreasing. Notice that magnitude is decreasing down to 0 because it's slowing down. And then as you move to the right, the velocity vector is getting larger. Notice it's always tangent to the curve, right? Okay, good. Now let's look at the acceleration vector. The acceleration vector, remember the velocity is slowing down. Oops, I want to just get the acceleration vector. So the acceleration vector is getting smaller. It's pointing in the negative direction because it's slowing down. Now the acceleration vector is getting larger. Notice the acceleration vector is always going to be pointed inward towards the curving of the motion, right? Inside the curve. Well, let's take a look at the animation. Let's have it all going at once here. So going from left to right, you see the acceleration is going to 0. Now the acceleration is getting larger. And the velocity vector is always tangent to the curve. The acceleration is always inward. Okay, let's look at this example here. So looking at the geometric interpretation here again, they want you to, a particle is moving along this path like this, and they want you to draw the vector that expresses the average velocity from 2 to 2.4. Now remember, the vector from 2 to 2.4 would be the change in the position vector, and then when you divide by 0.4, it would be a vector that looks like this vector, but it'd be a bit longer, right? Because you're dividing by 0.4. Similarly, if you want to go from 1.5 to 2, this vector here is r of 2 minus r of 1.5, and if you divide by 0.5, it would be this vector, but it'd be longer. Then the velocity vector at 2 would be a tangent vector at 2, and it would be written like this. And that's how you could look at it. Now, this is an important problem. This should actually be a theorem. If you have an object moving along a circular path with constant speed, suppose we're talking about this vector here. Notice this is moving along a circular path. Omega is the speed. It's constant, we're assuming. And a is the radius of this circle. So at t equals 0, you're here and you're moving along it like this, okay? And they want you to find the force acting on the object. Now, using Newton's laws, the force equals ma. So we're going to find a to do that. Okay, here we go. We're going to first find a. So if this is the position vector, this is the velocity vector. Now we're assuming omega is constant, so when you take the derivative of cosine omega t, you'd get negative omega sine omega t, right? We're assuming omega is constant. That's why this turns out. Otherwise, you'd have to use the product rule, right? Or the chain rule, I should say. You have to use the chain rule. Anyway, so this is v, this is a. So what is the force? Force would be equal to ma. That's an equal sign. Anyway, so it would be m times this. And what you notice is if you factor this out, this right here is r inside the parentheses. So you get negative m omega squared times r. So that shows that the force is opposite the direction. It's opposite the position vector. So for example, the position vector would be from here to here. The acceleration is going to be opposite that. Okay, that's interesting. It'll be pointed inward in the opposite direction of the position vector. By the way, this is also important. Since you're traveling around a circle, this is coming from 13.2, example 4. We've already looked at this. Since you're moving along a circle of radius a, since r has constant magnitude, we actually showed in 13.2, example 4, that it's the dot product of r with r prime, which is v, equals 0. That means that r is perpendicular or orthogonal to v. That comes from the fact that the r vector has constant magnitude. By the way, if it's moving around a circle with constant speed, that means the velocity vector has constant magnitude also. What does that mean? That means that v will be orthogonal to a. V will be orthogonal to a. So here's r going like this. Here's v orthogonal, and then since a is directed inward, right? So a is orthogonal to v as well. That's nice to know. Let's look at a couple examples here. Here's one. We're starting with the acceleration vector, and we want to find the position vector, okay? So we're given the initial velocity vector and the initial position vector. So when you integrate the acceleration vector, you get a constant. Now the constant is a vector, not a number. So when you integrate this, you get negative cosine I plus 2j plus 3k squared plus some vector c1. Plugging in 0 and using the fact that v0 is negative k, when you plug in 0, you get negative I plus 0 plus 0. So negative I plus the c vector is k, is negative k. So what is this constant c1 vector? c1 has to be I minus k. So you're going to plug in, you're going to add a 1 onto the I vector, and you're going to subtract 1 from the k vector. Here we go. Now let's go again. So the position vector is the integral of the velocity vector. When you integrate this, you get t minus sine ti minus 2 cosine tj plus t cubed minus tk plus some other constant vector c2. Now we're assuming that r of 0 is negative j minus 4k. When you plug in 0 here, you just get negative 2 times the j vector. So negative 2 times the j vector plus c2 has to equal this. If you solve this for c2 vector, you see c2 equals 3j minus 4k. So you plug all that in, and there's your position vector function. Isn't that great? I knew you would like that. Let's see a couple more things. This is the last thing on this video I want to look at. Laws of motion. I'm sure you've seen these from your physics class or maybe your pre-calc class. When an object is launched with an initial velocity vector v0, we're going to derive these laws of motion using vector functions, okay? So we're going to start off like this. This is kind of fun. We did this in Math 152, but we didn't do it with vectors. the force acting on the object is ma, and the only force we're assuming is gravity. So it's going to be negative g because it's pointed downward. Let's see. And anyway, so this is two-dimensional vectors, okay? So the j vector is the vertical one. Okay, anyway, so we do this, we integrate this, like we were doing before, and you get minus gt, the j vector, plus some constant vector, c. Then you can use the fact that when you plug in 0, everything drops out except for the c, so c has to equal the v0 vector. So now you integrate again, and you get r of t, you get negative 1/2 gt squared j plus t v0 plus some constant vector. When you plug in t, you realize that the constant vector is the initial position, which we're assuming is 0, the 0 vector. So we get down to here. So we're basically done. All we got to do now is look at the components of this vector valued function. We're assuming v0, if v0 is a vector, has the components v0 cosine theta I plus v0 sine theta, or I guess that's alpha, v0 sine alpha j. So when you plug those in for the constant vector, you get that r of t is this, and then if you break the into components, there they are. Amazing, isn't it? So some of those on the homework you might see. What I want to do is a problem like this. We're assuming now a three-dimensional case where a person throws a ball in the air. So you're going to have, in the k direction, you're going to have g. We're assuming we're in feet, so g would be negative 32 feet per second squared. But in addition, the person's throwing a curveball or putting some sort of acceleration in the j direction of 4 feet per second. So this is your initial acceleration vector. Due to the spin on the ball, you have this component as well. The question is, where does the ball land? All right, well, we're going to do the same thing. Look, we end up integrating the acceleration vector. You get negative 4tj minus 32ck plus some constant vector. And we're assuming that well, they're telling us the initial velocity vector is this. So when you plug in t, everything drops out except the c1. So this has to be your c1 vector. Now notice you're adding 50 to the I component, and you're adding 80 to the k component. So you introduce this 50i, but you also add 80 onto the minus 32 tk there. All right, now you integrate again, and you're going to get negative 50ti plus 2t squared j minus 2t squared j, I guess. And then here you get 80t minus 16t squared k plus some other vector, c2. Now we're assuming the initial position 0, so if you plug in 0 everywhere there's a t, we see that c2 is actually the 0 vector. So this is it. Now to answer the question, where does it land, you set the vertical component equal to 0, and you get t equals 5 seconds. So when you plug that into the position vector, you get this. Now, what is the speed? That's the magnitude of v of 5. So you plug in 5 into here. You plug in 5 into here for t, and you take the square root of the sum of the squares of these. You get that. I knew you'd like that. All right, well, that's about it for now. Oh, we'll talk to you later. Bye-bye.